Hi everybody, this is our supplemental video lecture on E2 regiochemistry. So let's consider the following E2 reaction. The first thing that I always do when I'm looking at an E2 reaction is I identify my alpha and beta carbons. Remember, your alpha carbon is the carbon where your leaving group is attached, and your beta carbon is one further away. We also want to identify beta carbons with protons. So for example, on this right carbon, we have a beta proton right there. We only have one beta proton for that particular carbon. For the bottom one, we've got this methyl group that actually has 3 different beta protons, but they are all equivalent because they can spin around in space. So let's do the E2 reaction for the top one. The base will come out, grab this beta proton on the right, clamp down, and kick off our leaving group. When we do that, we're going to get a new double bond between the alpha-beta position. We're going to get our conjugate acid, and our leaving group will be jettisoned off. All right, the bottom reaction is pretty similar, but this time we're going to go after one of the beta protons coming off the methyl group. That's going to clamp down and kick off the leaving group. When we do this, we'll get an alpha-beta double bond on the other side, and then the other beta position will remain untouched. And just like before, we'll get these byproducts as well. All right, so when we look at this, it's pretty hard to tell which one's actually going to be favored over the other. So when I'm asking which product or reaction is preferred, a lot of students will want to say this top product is more preferred because it's more substituted and more stable, but the answer is a bit more nuanced than that. So let's make a note of that and say it depends. Specifically, it depends on the size of the base. If you look at that example that I gave you, I had generic B. I didn't say what base we were using, but if we had a bulky base, that would give us different results than if we had a small base. All right, so let's look at a few examples where we use different size bases. And let's start out looking at an example where we have a small base. So let's say we've got a small base and we do this first reaction. Okay? In this first reaction, our base is going to reach over, grab this proton, clamp down, and kick off our leaving group. If we think about our transition state, the base is approaching this beta proton. It's going to form a covalent bond with it. And then it's going to break the covalent bond between that proton and the carbon to that beta position. And then we're going to form a new pi bond right there. And then our leaving group is going to get kicked off all in one step. All right, when we do this, we're going to form a new double bond in this alpha-beta position, giving us our tri-substituted product, right? So then we have to ask ourselves, well, what can stabilize this formation of a double bond? And if you remember in class, double bonds can be stabilized by adjacent sp3 carbons. So over here, we've got 2 methyl groups, and then on the other side, we have a 3rd methyl group. Each of these methyl groups will actually help the formation of that double bond. So let's just go ahead and circle that and then make a note. So let's say the formation of this double bond is stabilized by hyperconjugation. And if you remember, in hyperconjugation, what's occurring is these sp3 lobes will actually dump a small amount of their electron density into the p orbital overlap for the pi bond. So it'll actually help stabilize it as it's forming in this reaction. So we do have 3 methyl groups, each with sp3 lobes, and that helps stabilize it a fair amount. This leads to a lower activation energy for this reaction because the transition state is more stable. That's an important feature in this reaction, right? Let's compare this to the other beta proton, and I've actually got the whole reaction shown, but let's finish the arrow pushing. The base could come grab this beta proton, clamp down, kick off our leaving group. So this time our base is approaching the methyl group proton. It's going to form a covalent bond with it, and then break that bond between that beta proton and its beta carbon. Then we're going to form a new pi bond between the carbons in that alpha beta position. And then the bond to our bromine is going to be broken. Again, just like before, we want to stabilize the formation of this double bond. However, in this example, we only have one sp3 hybridized carbon to help stabilize that pi bond. So let's make a note here. Let's say that this transition state is less stable due to minimal hyperconjugation. This time we only have one set of sp3 lobes to help stabilize that pi bond. This will lead to a higher EA for this reaction because the transition state is less stable. Alright, so we've looked at the transition states, and then we previously mentioned if we look at the products for each of these reactions, in the top reaction, we're going to be making a more stable tri-substituted alkene compared to the bottom one where we're making a less stable mono-substituted alkene. So looking at all of the different pieces for this reaction, we would argue that in this top reaction, this one up here, not only are we going through the lower activation energy, but we're getting the more stable product. That means this reaction pathway is more favorable. Alright, that doesn't mean that the bottom pathway doesn't occur at all. It just means that it's less likely to occur. So the big takeaway from this is if we were to identify these products in solution, the top one would be listed as my major product, and the bottom one would be listed as my minor product. So we would get some sort of statistical distribution of these two products. Alright, let's try to make sense of this more using a reaction coordinate diagram. So in our reaction coordinate diagram, let's first focus on the left-hand side with our starting materials. In both reactions, we started with the exact same starting materials, so these are going to start at the same energy level. However, let's now look at the products. We know that the mono-substituted alkene is going to be less stable and higher in energy than our tri-substituted alkene, so we can stagger those. In addition, over here we said that one pathway went through the more stable transition state. That's the one where we formed our more substituted double bond. So that more stable transition state is going to be lower in energy than the alternate transition state, this one right here, where it was only stabilized by one of those sp3 hybridized carbons. That will be higher in energy. So like I was saying before, the key feature in this reaction is that this black reaction pathway, where we lead to the tri-substituted product, not only has a lower activation energy, but it gives you the product that has the largest drop in delta G. So this is a very favorable reaction. It's pretty easy to understand with small bases. Alright, where it gets tricky though is when we start thinking about what happens if we use a large base. So let's take a look at switching out to a large base. So in this example, we're going to be using a big bulky base, terbutoxide. Terbutoxide is really bulky due to the presence of 3 methyl groups hanging off of the back end here. Alright, so in this first reaction, the terbutoxide anion will grab the beta proton off the right, clamp down, and kick off our leaving group. During this reaction, just like before, the base is going to approach, grab that beta proton, rip it off of the carbon on that right-hand side. We're going to form a new pi bond in that alpha-beta position, and we're going to kick off bromine as our leaving group. Again, this will lead to your product over here that is tri-substituted and more stable. All right, so this would be more stable. Let's indicate that. This would be tri-substituted. and then we can do the next one. But let's go back and identify the features in the transition state after the second one. In the second reaction, we're going to grab a beta proton on the left, clamp down, kick off our leaving group, and just like before, the base is going to reach out, grab that beta proton, form a new covalent bond with it. We're going to break this alpha-beta position bond. We're going to form a new pi bond between alpha and beta. We're going to kick off bromine. So in the previous example, what we were looking at was hyperconjugation. So we said that these three methyl groups help to stabilize the formation of that pi bond. However, when you have a big bulky base, something else is also occurring that is really important and needs to be considered. And that is the fact that this tert-butyl group is going to physically run into these methyl groups hanging off that right-hand side, and it has a harder time physically approaching that beta position. That actually overrules and outplays the stability imparted by the hyperconjugation. So let's make a note of that. Sterics makes it harder for the base to reach the more substituted beta proton. This overrides the stability imparted by hyperconjugation. This means that the transition state for the top reaction is less stable, and it must have a higher activation energy. All right, if we look at the bottom one, for example, just like we said, sterics plays a big role. This time the tert-butyl group is kind of hanging out alone in space. It's really not running into any significant portion of our substrate. Therefore, it has a much easier time approaching less substituted beta protons. So we would say the less substituted beta proton is more accessible. This leads to a lower activation energy for this reaction because that transition state is more stable. All right, here's the irony though. If we think about the product for that bottom reaction, this guy right here, this is actually a less stable product. And it's important to remember it's less stable because it's only mono-substituted. All right, this is odd though, right? So we've got this conflict going on. In this top reaction, we're forced to go through the higher activation energy, but it gives us our more stable product. What's going to win out? What's going to drive this reaction? And in this reaction, it's actually determined mostly by activation energy. So if we think about it, the reaction that's favorable will have the lower activation energy. That means that this less stable product will actually be your major product in this reaction, and the top one will be minor because it's forced to go through the higher activation energy. It's a bit weird to think about. But let's take a look at reaction coordinate diagrams for this. Just like before, we're starting out with the exact same starting materials. And just like before, we said our mono-substituted alkene is going to be less stable than our tri-substituted alkene, therefore higher in energy. But this time, each of our transition states is going to be a little bit different. Okay, so let's focus on this transition state here. You can see I've got that steric clash highlighted in yellow, and I'll re-highlight it in orange just to make it more clear. In this one, we know it's going to be less stable, and it's going to be a lot higher in energy, so it must be that larger hill that we have to climb. The one where the tert-butyl group is sticking out and away from everything is a lot more stable, so this is going to be lower in energy right here. All right, So if we think about it, when we're doing a reaction, the reaction would prefer, under most conditions, to have the lowest barrier, right? So this activation energy is going to be a little bit lower for the transition state that actually leads to the less stable product. This is a weird situation, so let's kind of clarify this, and we'll just say that this, even though it's our less stable product, had the lowest barrier, and this will be major. And then this bottom one will be our minor product. All right, another way of thinking about this is kinetics versus thermodynamics. That blue pathway, meaning the one that led to this upper set of products, is under kinetic control. Or we would just call this our kinetic product. Kinetic products have the lowest EA. The bottom one, on the other hand, had a higher activation energy, but ultimately gave you your more stable product. This is referred to as your thermodynamic product. And in thermodynamic products, we don't look at activation energy. Instead, what we look at is the difference in delta G, right? So for that blue pathway, the delta G drop was about like that, where for the black pathway, the delta G drop was much more significant, right? So one could argue thermodynamically we should get our thermodynamic product, but one could also argue kinetically we get our kinetic product. The big takeaway with E2 reactions is the major product for this reaction is going to be less substituted due to the activation energy. And students have asked, well, what happens if you run this at high temperature conditions, as we do in a lot of elimination chemistry? Couldn't you theoretically trap yourself in this reaction pathway? The reality is not so much. Once you form this kinetic product, meaning you land in this kinetic well, it actually has a hard time going back out, doing the elimination reaction, and then reforming your thermodynamic product. So really, it's just going to get trapped here, even though it's your kinetic product. All right, so here's a short summary for this. If we look at using a strong small base, like in this top example, our major product is going to be our more substituted alkene, right? However, if you use a strong bulky base, as indicated down here, your major product actually flips. In both situations, you will get a statistical mixture product. The only change is which one is major and which one's minor. So as we covered in class, there are a handful of common strong and small bases. So let's take a look at those again. Common strong small bases are things like hydroxide, methoxide, ethoxide, and hydride reagents. All of these are relatively small and tend to favor your more substituted alkene. So let's make a note of that. If we look at bulky bases, if you notice in bulky bases, we've got these 3 methyl groups coming off here, got 2 isopropyl groups coming off here. The other ones, we've got these 2 giant ring systems coming off. So we've got a lot of steric heft for each of these bases. That makes each of these very, very bulky. So on the left, we've got potassium terbutoxide. In the middle, we've got lithium diisopropyl amide. And then we've got 1,5-diazobicyclo-430, known 5-ene, commonly referred to as DBN. And then in the bottom, we've got 1,8-diazobicyclo-540-undex-7-ene, commonly referred to as DBU. All right, all of these are so bulky that they have a hard time reaching the more substituted beta proton and lead to the less substituted alkene. All right, so try to remember what these bases are used for and when they're appropriate to use them for a certain transformation. All right, last but not least, we need to look at the historical context. So this guy on the right, August Hofmann, was looking at alkylating amines in particular. If you alkylate an amine and make it a cation, then amines become really good leaving groups. He noticed when he did E2 chemistry with these, he would get the less substituted alkene. On the other hand, Alexander Zaitsev was doing E2 chemistry with smaller bases and noticed that he tended to get the more substituted alkene, however, he was using different leaving groups. These names have historically stuck, so whenever you see Zaitsev, you should immediately think that's the more substituted alkene. Anytime you see Hoffman, you should think that's going to be my less substituted alkene. So let's go ahead and fill in our notes up here. If you think about using a strong small base, we said we would get our more substituted alkene. That favors our Zaitsev product. In fact, we could just say Zaitsev product in quotes here. For the next one, we said that strong bulky bases favor our less substituted alkene. That's our Hoffman product. All right, again, let's go back up in our notes. If we look at the more substituted alkene, that's always our Zaitsev product. And our less substituted alkene is going to be our Hoffman product. It is important to remember that your Zaitsev product won't always be major, right? We saw down here, when we use a strong bulky base, our Hoffman product can be major, and in fact it is under most circumstances. All right, I did post a good set of practice activities on the class website, and the answer key is posted in OneNote as well. However, if you have any questions, you're more than welcome to email me. Good luck studying.